but there were many model evaluation matrices, as I told you last week, and then we went through a KNN regression, but we did not go through hyperparameter optimization model, which we'll discuss today, and then KNN and decision tree. I think I started from here. Sorry, I stopped the lecture from here, random forest, explaining how it improves the decision tree. So today we'll move into ANNs. So this is some kind of debatable topic among the machine learning models, because some of the machine learning researchers say, like, they divide machine learning models into classical machine learning and deep learning. So some people strictly says that all the models other than ANNs belong to classical machine learning, such as linear regression, KNN, decision tree, random forest, and support vector machine, and ANNs belongs to deep learning category. But for the deep learning itself, um, there are other conceptual frameworks, such as we need to extract important features, bit of feature engineering, which might not be possible in a simple neural network. So that, again, simple neural networks belong to classical machine learning, but it's only a conception. You don't need to worry about that. What we need to worry is how ANN works. So ANNs are inspired by the brain of humans, how the human brain works. ANN tries to mimic that process. So if you see a brain, there are millions, or else maybe more than millions, I don't know the exact number, of neurons connected to each other. So they pass the signals and taking a decision. So when you see a car, if you have been taught it's a car, okay, your brain automatically identifies it as a car. And if your brain has learned the colors, okay, when you're in grade 1 or 2, or else before that, your parents or else your teachers show you colors and say that, okay, this is yellow, this is red, so this is blue. So have you ever thought why we are saying it's blue? Just because simply someone has trained us to do so. If someone said, like, showing red color at that time showing red color, and trained you, it's not red, it's a blue color. So at this moment also you will be saying exact same thing. So not, it's a blue color. So simply, at the beginning, when you were childhood, you were acting like an untrained model. So it's your teachers and parents who trained you. So similar set of working is applicable in artificial neural networks, which were developed later. um, so they use the same concept of neurons connected using these connections, and within few layers or maybe multiple layers, to be developed as a network. So once you give set of inputs, uh, sorry. So once you give set of inputs into the network, using these layers and their neurons and their connections, they will perform specific calculations and come up with a certain predictions. So how does this prediction come out? is what we are interested of. So if you isolate only a neuron, so there can be uh, multiple or maybe thousands or hundreds of neurons in a neural network. So only we are considering these specific neurons. So if we have three inputs, let's call x1, x2, and x3. So simply there will be weights associated to each of these inputs, say W1, W2, and W3. And what it simply does is they take is inputs into the weights and their summation. Say, for example, this y value obtained from here is x1 into their respective weight and plus x2 into their respective weight and x3 into their respective weight and addition of the uh, sorry, Chamod, I got your message. I cannot see any recording options. I don't know.
So, sir, is this only recording in my computer, or earlier I saw there was a cloud recording
Yeah,
option as
I can see it's been recorded,
ah
but
okay.
will it be saved in yours or
Yeah, yeah, this will be saved in my computer, and
okay
also
then
then it's
okay
okay.
then
Yeah,
there's no issues, right?
sure.
Okay.
Yeah, yeah.
Okay. So if someone has a screen recorder, he or she can record as well just in case. Yeah. Okay. Yeah. All good. Let's go to the session. Sorry. So again, back to the neuron. So this kind of an operation is happening with this unit called neuron. So why does it matter? So when these neurons are connected, so you can see how complicated these connections become when there are thousands or hundreds of multiple neurons with multiple layers. So this we called a hidden layer. So Z1, Z2, and Z3. And this we called input layer, which consists of three inputs. The advantage of neural networks is it can give you simultaneous multiple outputs as well. Unlike in a decision tree or support vector or any linear regression other models. So that can only give you a single prediction. So if you need multiple predictions, that means there should be multiple models. If you have three outputs, you should train three decision trees. You should train three different SVMs and KNNs, but a single ANN can accommodate all these outputs at the same time. Is that clear to you all? Any questions up to now? You can use the chat if there's any
Yes, sir.
issue. Okay. So I have given information of what is this bias and activation function. So once we get this neuron value, this will be sent through an something called activation function, which is one of the important parts of the FNA ANN because that adds the nonlinearity to the neural network. So there are a bunch of activation functions which we call unit step and then linear or the piecewise linear, ReLU, and so this horizontal axis will give you the value coming out from this operation, and that will go through the activation function and give uh, the function value for that respective value. If you use a hyperbolic tangent, so this z, sorry, uh, this z is the value coming out from that operation in the neuron. So based on z, you can just calculate this function value. So that will travel through the network for the other iteration. So I will show you how that happened. So there's another concept. While we are focusing on training a neural network, something to do with loss. So I'm sure that Dr. Samiru has introduced you what is loss function, which we can introduce as simply the error or the difference between the predicted and the actual value. So the actual output is the prediction coming from the neural network. So the desired output is the observed or actual value, actual y value. So based on its error, so that error will be given to the network to optimize its network weights and biases. That's how simply we can put it to how ANN works, how an ANN works. So this is a summary of how it will. There are many mathematics and operations, especially calculus, chain rule, and gradient descent optimization, which is associated with how to calculate this weight. I'm sure I sent you a video, so you all need to consider watching those additional at least 2 to 3 videos if you are interested how this works, because it's not like a simple decision tree. So now if we consider about linear regression, so having all these inputs x1 to xn, what it does is using the least sum of squares, it fits a linear model. So that's the whole operation. So if it's a KNN model, what will happen? Now you know. So you provide it the value of, or else the number of neighbors to look at. Number of neighbors to look at. So the KNN will choose the nearest neighbors based on a distance and will give you the prediction which just looks like an interpolation. So in a decision tree or else in a tree-based models, so those models work based on the impurity of the data. So they separate small variance within the data into subgroups. And once the tree is obtained, whatever the inputs go through a particular branch, the average at the end of the tree or along that branch, which you call the leaf node, will be your prediction. So if you need more and more accurate predictions, I ask you to improve its depth or else optimize the depth. But there's a risk when you increase it too much, model can easily become overfitted. So I told you how to select those depths, which we using 2 to the power n. So simply 2 to the power n should be fairly small. I mean, maybe significantly smaller than the actual training data set points. Now here, when we have x1 and x2 and xn, all these inputs, it will go through this operation at each neuron. So once we get this value, it will go through something called an activation function. So all these neurons and these all these activation functions, like in a single circular, and now we have thousands of these or maybe hundreds of these circulars units connected to each other. And maybe we can have hidden layer, I mean layer 2 layers, 3 layers, or 4, 5 layers. Sometimes we try to introduce a model as a deep neural network if there are more than 3 layers. If there are less than 3 layers, we call it a shallow neural network. Um, and if more than 3 layers or more, we call a deep neural network. But it's not strictly hold as it is, because there are other types of deep neural networks as well, which belongs to computer vision techniques. So just keep that in mind. So finally, with these operations, then now we received its output. So from each tree and each linear regression model we created, K, N, O, whatever. So we all came to this point. So we got the prediction. Now what? So what the network does is, so using this y value, we calculate the loss. So it's simply the difference between the actual, what it should be, and the obtained y value. And using that error, we back propagate it. So which simply the gradients of the loss with respect to each weight at each layer. So we does it using, that's why I ask you to go through the chain rule, which we learn using, I think we learned it using, during our A levels, and then using gradient descent to optimize or update the weights, new weights. So new weights is usually the old weight minus zeta, and the differentiation of loss with respect to the weight. So this uh, symbol what we use is the we call learning rate of the neural network, and we updated these weights, and this will be repeated for number of iterations, so called epoch. So there are many complex terms, don't worry. If you I mean this is a very slow process when we are learning neural networks. Say for example, in my case, it took me around few months to learn the classical machine learning, decision trees, support vectors, and all those stuff. But it took me more than 1 year to learn how an ANN works, because we don't have the background mathematics related to that. And once you are going to learn how this works, okay, this component is needed. To learn that component, another component is needed. So likewise, it's a bit of searching and self-learning. But we'll do a simple neural network and see how it goes with the same concrete data set. Let me. Okay, okay. Do you have the same concrete data set I shared last week? Hello. Do you have the same data set?
Yes.
Okay. Let's then. Okay. I will give you a simple task now. So what you need to do is read that data set, same set of variables, and I'll send you the link now. Okay. So your task is um, open the data set and fit a random forest model and extra tree model. So I will send you the links to for those codes if someone required, but it's in the chat. So this is for the extra tree regression, and this is for the random forest regression. And let me know which model achieved the best accuracy, or else maybe R squared, mean squared error values. And finally, try this model, XGBoost. I will send you the code for that. Sorry, I didn't share anything. I send the links in the chat for you to try. Is that clear, Nisal? So you will have all the required libraries called upfront so that you don't need to call them later, and open the data set and columns. So while you are doing it, let me recall important notes. So always check for statistics and correlations between inputs and inputs and outputs, and see whether there are redundant variables that you can remove from the dataset, which can be either constant values throughout the dataset. So if there's a variable which you call as an input, is a constant through is a I mean has a constant value throughout the dataset. So model cannot learn any pattern from that variable because it's a constant throughout. So in that scenario, we usually remove it from the input data sets. Let me know the accuracies you obtain for random forest and extra tree and XGBoost, and let me know which is the best model. So one important note is the last model, the XGBoost algorithm, is not available in scikit-learn. So it's from a different source uh, called XGBoost itself. So I have provided the link for that, so you can get the code, which is step five in that code. Very similar. I mean, similar set of codes that you use it because once you import the model, when you have defined the X train and Y train sets, it's just fitting the model. I mean, computer will do it for you, but the optimization depends on your effort and your experience. Anyone, anyone obtain the random forest or extra tree accuracies? Use the chat. So, what are the accuracies you obtain for a random forest or extra tree? Any issues that you have while training the models? Anyone? Any problems? Has anyone fitted the models? I can't see any results from anyone. Okay, I hope you can see my notebook. Can anyone confirm?
Yes.
Yeah, okay. So the same way, so we define the data frame as DF, which includes the data from concrete.csv file. And for the columns, I have seen so cement, blast furnace, all sort of columns are there in the CSV, which I used as inputs and outputs, which is the target value of Y. And then I have divided them according to the 70 to 30 training testing split, where 70% of the data goes in for training and 30% for um, testing. So what I need to do is now um, develop the random forest model. So what I can do is, if you haven't called random forest in the beginning as a library, so what you need to do is from sklearn sample, you need to import random forest regressor. So once done, you can create any name for your model. I will call it RF. With the same random forest model. Maybe I will use max depth So these parameters are there in the scikit-learn page I told you last week. So I'll just use 3, and then what I will do is this rf dot fit x train y train, which were my x training set x and y. So if I fit this one, yeah, now the model is fitted. So how can I compute its r squared value? So you should have imported these scalar matrices beforehand. So I would print, I think I haven't called them, that might be an error. Let me see, check. Mean squared error is there. Print testing mean squared error equals, so mean squared error function. So what I need is y test and the predicted model is rf dot predict x test. Bracket. See that works? Yeah. So you can do the same for training set as well. Squared error y train. Train. We see r squared works for this one. So what are the r squared values you obtained? Anyone? Not even single. What was the best r squared you obtained? I obtained around 0.71, zero point 0.7, yeah, zero point 0.7. It's not overfitted, but it's not very good model. Has anyone obtained a model better than this? Okay. Can anyone suggest me in that case how to improve this model? So now I obtain uh, a random forest model, which is a tree-based model, um, with an R squared of 0.71. So anyone has any advices how I improve this model? So this reflects the things that you learned last week as well. Training set can be 80%. Yes, it can be 80%. No problem. No issues. It doesn't need to be 70/30, but it is something that you need to do trial and error and figure out which is the best training testing split. So most of the research have been successful, or I would say become successful by using 70/30 split, but it doesn't guarantee that like it's the ultimate training testing split that you should use. So always make sure the distribution of y value is, I mean, the target is comparable between the training and testing. Otherwise, you might be doing something pointless, because ultimately what you are predicting is, or else what are you trying to do is to fit that distribution. Having said that, anyone to suggest me how I can improve this random forest model? No one. So okay, let me put it this way. So I told you this is a tree-based model. So I told you few important parameters that you look in a tree-based model. What are those parameters? Okay, by changing hyperparameters of the model. Yes, good answer. Which hyperparameters should I change? If it's a tree-based model, if it's a decision tree, what's the best hyperparameter that you can change and see? Yes, max depth. Yes, max depth. But for decision trees, I don't think you can change the estimators or tree number of trees because it's a single tree. So now I will use a max depth of 10. So when by doing that, I will make sure. So 2 to the power 10 is how much? 1024. 1024. And how many training data we have? So it's like 693. Can anyone suggest what will happen to this model? Okay, I will use 12. Can anyone suggest what will happen to this model? Will this be a good model? Yes, maybe, maybe, yes. But let's see. So as exactly what we expected, what has happened? Model has become overfitted. Now, I mean, now can you explain why this was overfitted? So even though random forest uses many trees, since our number of data points or data rows in a single data set exceeds the number of bags, or is what we called leaf nodes in a tree. Okay, so there can be at least one data point in a leaf node when we are taking the average. So taking an average from a single data point or maybe 2 points is extremely sensitive. This is why it's gonna get overfitted. So what's the safe depth for this one? If someone suggests, yeah, yeah, I can see some of the answers. Yes, very good. Their reasoning is 100% correct. So what's the safe depth I can use for this random forest? Anyone? So can I use 6? Okay, 9, yes. Let's see, 9 and see. What about this model? Is this good? So the training error is 4%, and testing error is, I would say, 11%. It's almost 3 times. Still not. Let's go with 6 and see what will happen. Okay, this is fairly okay, but tend to be overfitted, but it's 91 and 86. Let's go with 5. Yeah, it's sufficiently good model. Now let's add estimators and see what will happen. Estimators is number of trees. I would say 25. Nothing changed. So that means mainly depth has already governed the tree. Let's go with 6. 7. So it didn't make a big difference. So I would select either depth of 5 or 6 for this model, but we didn't perform any optimization for this. For now, I use depth of 5. If someone wants depth of 6 is also okayish, but not so much. But having look at the mean squared error values, it's like, yeah, I would go with 5. So I will come to XGBoost model now. So I will go with same depth, number of estimators without these things. Let's go. What about this model? Sarah. Is this a good model? What about this? Usually XGBoost has boosting, which we call like based on the error of previous tree, the next tree is improved. So for this reason, XGBoost model at the same depth can be, I mean, I wouldn't say 99% of the time, but at least 80% of the time, XGBoost outperform many tree-based model and many classical algorithm, even simple ANNs. So this is one of the best um, state-of-the-art models, which we call extreme gradient boosting. And a similar conceptual framework is there in a light gradient boosting model, or else categorical gradient boosting, which we call cat boost. So today what we are using is XGBoost model. So can anyone tell me, is this a good model? Training score is 99 and testing is 92. Is that a good model? Anyone? So this is again an overfitted model. You can see the training scores 99, 92, and mean squared error, especially the testing is, uh, sorry, mean absolute error. Sorry, it should be, sorry, I haven't given the training values over here. Sorry, it's squared value and mean absolute for testing only. Let's get this one for training. So what we need is training mean squared error. Training mean squared error. Excuse, this should be train. This should be train. And same goes with mean absolute error as well. Training mean absolute error is X train, sorry, Y train and X train. Let's go. Yeah, it's not a very good model. Its training error is 59, almost become double for the testing case. So it's still with max depth of 5 and these parameters. Let's see with just only max depth. Yeah, you can see it's highly overfitted. Training mean squared error is 1%. It almost becomes 17% for the testing set. Once we include uh, gamma and number of estimators, let's say a random number of 100. Yep, still not going to work. Let's reduce the number of trees in the forest, 30. So 91, 92. Overfitting is slightly reduced, but not so much. Let's go with 12. 94, 88. I mean 89. Not that bad, but still some overfitting is there, slight overfitting, but it's not a very bad model. So so you will realize doing these iterations by hand is a, I mean, it's a pain because you don't know at which parameter, which value would this XGBoost regression will give you the optimum set of solutions which are not overfitted. Okay, so for that, what we usually use is, sorry, before going into that, something called, let us go to the presentation again. Can you see my slides?
Yes.
Yeah. So for this one, we will be using this hyperparameter optimization, which I did not go through last week. So the main concept is we need to select number of hyperparameters that we want to optimize, and we need to identify their best set of values that will give you the best performance. So that best performance is something that you have to define. Either you can select, okay, give me the best R squared value, which will give you highest training accuracy, or else you can suggest which is the best set of parameters which will give us um the highest testing accuracies, or else, if I were you, I would suggest give me the best set of solution, best set of parameters that will give you the highest R squared for training and testing, and as well as a minimum gap between training and testing errors. That is something you should be aware of, getting the model not overfitted. So it's not about the highest training accuracy or either train testing accuracy. It's always the balance between these two sets. So training accuracy, testing accuracy should be high, yes, but there are difference. So their difference should be extreme. I mean, as much as low. If their difference is larger or significant, that means either model is going to be overfitted most of the case or is underfitted. Underfitted is testing accuracy becomes way very much higher than the training accuracy. Okay, so and over here, the first method out of these three methods, which are regularly used in machine learning and applied machine learning, which we call grid search, random search, and Bayesian search. Let's assume a random machine learning model having hyperparameters as x1 and x2. So these are not model inputs. X1 and x2 are hyperparameters, something like tree depth and number of estimators. So I suggested we need to check depths from 1 to 10. So someone can suggest, okay, x1 can vary from 1 to 10, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the tree number of trees, which is x2, can vary from, I would say, 10 to 200 in 30 or 50. Or else I'll pick random values like 30, 50, 100, and 200. So you would see for each pair of x1 and x2, there would be a separate machine learning model. Is that understood? Is that understood to you? So each pair of hyperparameters we can fit a separate machine learning model. Is that understood?
Yes.
Yeah. So having said that, if you have 10 parameters for x1 and 5 parameters for x2, that means you will have to fit 50 models to evaluate this entire grid. Now think about when you have 5 to 10 hyperparameters or 5 hyperparameters with each having five different values. So it's 5 to the power 5, I think, if my computations are correct. So that will be a huge number. So when you increase this grid or the values in this grid, it always concern about the computational cost. So if you have a large grid, the models need to be evaluated for each coordinate within that multi-dimension grid. So don't worry about the multi-dimension word. So now it's two-dimensional. So when you have three hyperparameters, it's three-dimensional. So beyond that, you can't imagine what it be. So we call it multi-dimension. So it has more many dimensions like x1, x2, x3, x4, x5. So those we call dimensions. So in that multi-dimension space, each ordinate will tell you a hyperparameter configuration, let's say x1, x2, x3, x4, and x5, or else x1, sorry, I should not be calling them x1, x2, let's say alpha, beta, gamma. If I say alpha, beta, gamma, and delta, so one combination can be alpha 1, beta 1, gamma 1, delta 1. So other one can be alpha 1, uh, beta 1, gamma 1, and delta 2. Likewise, many different configurations. So for all these ordinates, we need to run a model and see what's the optimum solution is. But it guarantees that you will obtain the optimum model if it's defined in the grid. But it will take time. For this reason, some of them uh, have been using something called random search. So what random search does is, okay, what random search does is, so we give the grid, but it will select random combinations out of that grid. So it will drastically reduce the computational cost, but it does not guarantee that you will end up with the optimum, but something closer to the optimum. If you have the optimum value, you can manually uh, change some values and see what's going on and pick up the optimum model. But nowadays we use something called Bayesian search, which runs on a Bayesian probabilistic model. So what it does is it initiates a certain combination. Based on that, it it guides the optimization process towards the optimum based on its error or the loss within few steps. So this is very computationally efficient, especially for models like neural networks. Rather than searching all the grid search, so you will see when you are fitting a neural network model. So let's go for to the. So any questions you have on these three definitions? I know that we didn't do any example, but do you have any understanding how this optimization is carried out, how to find this evaluation? This is what you should be doing when you want to train a model. It's not that random parameters that we did last week. There should be a proper optimization which we couldn't do last week. Is that clear to you? Sorry, I can't see the chat. Anyone, is that clear or not? Or do you want me to repeat?
It's clear, sir.
Okay. Okay. Let's go to the notebook again. Can you see the notebook?
Yeah.
Yes.
Okay. Um, okay. So I will use the XGBoost model to show how that optimization process is carried out, but still not, this is not the proper grid search or random search. Just I'm trying to show you, if you see that those methods are time consuming or difficult, you can adopt this method as well. So what I did was I developed base parameters for the XGBoost model. So I have a base model. So this is not something optimized. So that base parameter or the base model is developed using max depth of 3 and estimate 100 estimators, so 100 trees. So learning rate of zero point 0.1, reg alpha and reg lambda are the parameters that you can control the O of it. Just keep it in your mind. Whenever your XGBoost model is overfitted, you can get it corrected or you can get it sorted using these reg alpha and reg lambda parameters by using only by optimizing these two parameters. You can easily get it into a good fit and a random state, which is a random seed. And what I would do is now, so I have developed using evaluation function for the XGBoost model. And first, in the base model, I'm keeping everything else constant and change the depth, which is max depth, as you can see here, from 1 to 11. 1 to 11, I'm changing the max depth and I'm plotting what would be the training and testing R squared with each depth. Here I only use R squared, but you will see why. So here I'm changing only the max depth and see what would be the training and testing R squared value. So in the next set of parameters, so I'm changing the number of estimators from 10 to 200 in the intervals of 10 and doing the same while keeping others constant. So if you say this is I, so I is changing from 10 to 200 and 200 uh, in intervals of 10. It's like 10, 20, 30, 40, likewise. So once that is performed, that loop is performed, other parameters are remaining within the base parameters. So whenever one is changing, other stays fixed within the base parameters. It's like I'm taking one at a time and change and see. So if I run this one, I will show you something else. So now I can see this XGBoost model. Okay. So the base model. So now, based on what you have learned up to now, can anyone suggest what you will choose for the depth of this tree? Two. Why is two? Yes. From what you have learned, it's true. So what I told was we need to get the maximum R squared and for training and testing, which is possible, and their gap should be minimum. Okay. So from that perspective, the best depth you can choose is 2. But I already told you this model, even if it's overfitted, you can control the regularization parameters and control its overfitting. So if someone wants to go with a higher depth, let's say uh, even depth of 4 is also possible. So you will see it's like 91 and 96. Okay. But you should never go with depths beyond 6, which you can clearly see why. So it's going to fit into every local variation in the data set and overfit. So as you said, yes, Adnan, your answer is correct. Some depths between 2 to 4 or 2 to 5 is okay, but given that you should optimize and control the overfit. Otherwise, I would, if I want to select depth only, I would choose 2. Is that understood? But always you can go for depths like 3 or 4 and properly optimize. Now let's see what will happen with the number of estimators. So you will see what's the number of estimators that you can choose. So it's somewhere like 100. So when it's getting converged, and you will see the gap between them are very minimum. So it doesn't matter even if you choose it's like 75 or 125. So that would give you a good uh, prediction for your model. And then the learning rate. So this is how fast your learning um, is done simply, but what's the best learning rate for this one? I would choose somewhere around zero point 0.2 to zero point 0.3. Not zero point 0.3, even maybe somewhere in the range of point 1 to point, yeah, point 1 to point 0.3 would be okay for me. Other than that, it's not going to be good for the model. And then let's see for the regularization parameters. Can't see much of a difference because of the axis arrangement I have shown, but it's not a very big gap, even though it looks like it is. It's mainly because of the axis arrangement I have shown here. It's a bit of exaggerated. So it's 0.935 and 9, which is okay. And over here, it's the same regularization parameter. So now I will do a grid search. So in this method, I'm calling again the importing the XGBoost regressor from scikit-learn. I'm importing grid search. Okay. So XGBoost model, this is not the base model I have used earlier. It's a different model. So parameters grid I'm giving. So max depth can be 2, 3, 4, 5, 6. And number of estimators 50, 100, and 150. And learning rate, I have given 4 learning rates. Okay. So, so within each, you will see something CV is 5. So CV means cross validation. Okay. So cross validation means when you have training set. Okay. For now, what we had was training and testing. So I'm sorry, now it's getting a bit more complicated. So what we had was training and testing. So within the training set as well, so if you are using model to learn and optimize through the same data, okay, so it's something like this. Let me draw you. Can you see my presentation? Or it's the white screen? Anyone? Can you see?
Yes, sir. Yes, sir.
Okay, all good. Don't worry. After this one, I'll give you a break, short break. So now what we did earlier was we had 70 to 30. So 70 goes into training and 30 going into testing, right? So now we learned something called optimization, which we did not focus last week. So when this optimization comes, model needs to learn and optimize its parameters using this data. So someone can say, since the model optimized, also using the training data, it can be biased towards training data. This is why people further divided these splits, say for example 60, 20, 20. So 60 goes for training, 60, 20 goes for optimization, which is another unseen test, or else we call this validation split. Okay. So training data set, training, and this is for validation, mainly for cross-validation, and this is testing. So this cross-validation set we use mainly for optimization. But what happens if we don't have enough data? Rather than doing this one, there's an efficient way. So for now, is this understood? Everyone, is this clear to you? Any question you have? Hello,
Yeah,
is that clear to you all? You can use the chat. Please, I
it's
need to
clear.
make sure that um, you have understood these concepts. Anyone who wants me to repeat? Is everything okay? So now, especially when we have, mm, yes, especially when you have smaller data sets, we would not have enough data to split into three groups. So that leaves us some option called fold cross-validation. Okay. So we learned something new today, which is called K-fold. So let's say this is the training data set, okay, which equivalents to 70%. Don't worry about this number 70%, okay? It's just a number, 70% is there. So now, if we don't have enough data or else enough data, in your opinion, to further divide it for training and validation, what you can do is this k-fold uh, cross-validation. So it will divide it to 1, 2, k folds, k number of folds. So this loop will run k times. Okay. In the first loop, that will use all the k minus ith up to k minus ith data and train the model and evaluate it using kth set. So in the next set, that will use from 2 to k and will be evaluated using first fold. So always k minus 1 sets are given to training, and a one set or else one fold is kept out for the validation, which we call k fold. So if this is 5 fold or 10 fold, so this means the data set is divided to, training data set divided to 5 folds. Now, in the first iteration, so 1, 2, 3, 4 is are used for training and evaluated on 5. And the next iteration, 2, 3, 4, 5 is used for training and evaluated on 1. And in the next one, 3, 4, 5, and 1 are used for training and evaluated on 2. Likewise, this will be repeated 5 times and we'll get the average across each fold. So for each fold, we'll get training and testing accuracy. Is that clear? Is that clear to you? Or it's a jargon? Can anyone tell me, please? Okay. Okay. You are saying yes. I'm not sure. Is it a Did you say yes for what I asked? It's a jargon, or is that clear? Okay. 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 Let's go to the notebook again. So this cross validation, uh, nothing new, but it's something new for you that you learn when you have what you have to do when you have less amount of data. So if I go to the notebook again, so for each of these trees. So now can anyone say how many trees this will create considering these parameters? How many trees it will create? Anyone? So it's a grid search. I have given 3 hyperparameters and their values. How many trees? Sorry, I can't see. The answer is in the chat. Okay, 60. Okay, 60 models. Okay. Now I'm doing a cross validation of 5 as well. So what does that mean? So this 60 multiplied by what? Yes, exactly. It's 300 models, evaluated, because for each model, there are 60 unique combination of hyperparameters. But for each combination of hyperparameters, you are sorry, it's not 300 models, it's 300 loops of iterations. Only 60 unique models. But since we are using 5-fold validation, so evaluation will be done 5 times per each unique model. Is that understood? I don't know who replied that. Sobo, did you get that point? So now what I'm doing is now I'm giving the grid search, and estimator is the XGBoost model I have developed over here. And parameter grid, I have equal to the parameter grid I have defined over here. And scoring, I will be using it is R2 squared. And number of cross validation is, the k-fold is 5. So these two, no, you don't need to worry for now, but if someone need, you can read it. And grid search, I'm asking to fit X train and Y train. So in this optimization, you will see I'm only using X train and Y train. Okay. So there are various ways that you can optimize this one. So it doesn't guarantee that this will be the optimum model just because I'm using training X train and Y train only. So we'll use this one, fitting 5 folds for each trees, totaling 300 feet. And you can see if you usually fit an XGBoost model, it will be fitted and give you all the answers within 1 second. Now you can imagine almost more than 20 seconds, almost more than maybe 30. Yeah. So that will give you max depth is 5, number of estimators is 5, learning rate is 2. Now, doesn't mean that this will give you the parameters based on its evaluation, which is on training and train and Y train. So now, would you accept these parameters? For example, learning rate 0.2. Now go to learning rate 0.2. Yes, I can accept it because there's less gap between training and testing, but we did not consider that as a fact during our grid search. We only considered the training and training scores only. Okay, so just be careful. Max depth of 5. Let's go and see max depth of 5. Okay, max depth is 5 over here, slightly getting overfitted. Okay, let's go. And number of estimators is 100, which was okay. So this would be a good candidate, both this method, grid search, and as well as this manual optimization, if you want to see how each parameter works. And based on that, get your best parameters. If I see these both, I would get maximum depth as 3 or 4, in my opinion. Not 2, because I know that XGBoost model can be improved using these parameters, which we call reg alpha and reg lambda. And max depth is a critical parameter. So this is how we manually optimize it and get an initial starting point for the model. Because for me, I know this, I have used these models and I have learned these models for 3 years, and I know, okay, this can be controlled via it, but for some of you that could be mostly the first time. So you need to make sure you understand each parameter and what those parameters are for. So I would strongly suggest, if you are going to develop or optimize a model, go with this manual optimization first and see what are the strong dominant parameters. So all the hyperparameters in sklearn are not strongly influencing the model output. Even if there are 20 to 25 parameters, there can only be maybe 3 or 4 parameters. Say, for example, in KNN, parameters like nearest neighbors and the distance can mostly govern the performance of the tree. There are other parameters as well, but mostly, okay, not 99% of the time, at least 80% of the time, the number of neighbors and the distance govern the performance, and I showed you last week why. And in the trees, especially decision trees, which is a single decision tree, the tree depth matters. Okay, tree depth matters. Using depth only, you can easily optimize an initial model. Now, when it comes to ensemble models like random forest, XGBoost, light gradient boost, cat boost, or as extra trees. I'm not sure extra trees has a number of estimators, but it should have. But I couldn't check for longer time. Especially again in ensemble models, parameters like tree depth and number of estimators can easily uh, tune your model. I mean, even if you do manual iteration, you can easily optimize using tree depth and estimators only. But if something like some model like an XGBoost, which considered as the best model in state of the art so far in most of the studies, if it's going to overfit, one thing you can do, check the data first. If there's an outlier, remove it, or else check the distribution, remove whatever the data falls from 2 standard or 1.96 standard deviation from the mean to either side. Even if that's done, still the model is overfitted. What you can do is control the tree using reg alpha and reg lambda. 100% that works. Most of the time you can control the overfit using regularization parameters. That's what they are for. And learning rate often. So models like support vector machine mostly strongly dependent on the kernel function you use. I've been using mostly RBF kernel, tell you the truth. So not the polynomials. There's a parameter called kernel. So under that you can use different kernels. I would usually use RBF kernel and the C parameter, and there's another parameter called gamma. Using those three parameters, you can mostly optimize a support vector machine. But when it comes to ANN, no one can tell you which is to be optimized, which is not even you, which is even if you ask some machine learning expert, he can't tell you which is the exact governing parameter, which is why it's very complex. And let's go and see why. So, do you understand that concept? How you should optimize and what methods are available? So, we only use manual optimization and then grid search. We didn't use random search. If you are using machine learning models for a certain data set using a new algorithm, first method you should do is do a manual optimization, even if you ask ChatGPT or similar AI tool to give that code to you, that will give you. And select a base model and try to understand how each parameter affects, and then decide, okay, what parameters should I optimize? Because if I hadn't done this step, I would have not known which parameters to optimize. So without knowing that, if I use a larger grid over here, that would take a longer time. So did you understand the difference between these two codes? Using manual iteration, you can identify which parameters affect, and you can you can minimize the size of that multi-dimension grid, and which can be used for the grid search. Is that understood or not clear? I'm happy to repeat it if you are not clear. Okay. Okay, someone asked me to repeat. So now let's say you have a new model, okay, which you entirely don't know which hyperparameters to use or which hyperparameters should I evaluate. So even though I told you to use a grid search or else a random search, there can be 10, 15 parameters to be optimized. If you are going to optimize all these 10 or 15 parameters, at least by using 5 parameters per each parameter, okay, that will give you 5 to the power 10 or 5 to the power 15 number of models to evaluate. Is that clear to you? Okay. Now, instead of doing that, which is computationally exhaustive, either you can use a random search, but still 5 to the power 10 or 5 to the power 15 is a large number. So what I did was I learned how each parameter works. For that, I don't need to use entire grid. I change only one parameter at a time. Even I can use 10 values per each parameter. So keeping other parameters fixed as we used base parameters. Okay, let's say we have alpha, beta, gamma, delta. Base parameters are 100 for everything: alpha 100, beta 100, gamma 100, and delta 100. So now I want to see how alpha influences the prediction. So I'm changing alpha from 1 0 to maybe 200 or 500 using certain intervals. So still that is less computationally expensive. Through that I can identify from their R squared values. Okay, if I change this one, see this, you saw that the how trees a number of the maximum depth affected the model prediction. So it's like a sudden increase, then converge, right? So it's something strongly influences the tree model, such as number of estimators. From that, by investigating all these 10 or all these 15 hyperparameters one at a time, I can learn, okay, what are the most effective ones. Let's say those 10 or 15 I can bring down to maybe 4 or 5. Is that understood? Okay. Now, once I get into 4 or 5, now I can use the grid search, because now instead of 10 to the power, sorry, 5 to the power 10 or 5 to the power 15, now it has become 5 to the power 4 or 5 to the power 5, which is computationally inexpensive compared to the earlier grid. Is that understood now? Okay. Okay, great. So you will understand why these grid search or optimization doesn't exactly go as it is as we are thinking for neural network models. So let's go with the same data set. Do you want me to share the code with you now so that you can also do it with me? What do you suggest? Yep, I'll share you. Wait. Sorry, before that, I'll give you a break. Sorry. It's been 2 hours, right? Sorry. I'll give you a 10 minutes break and then we'll continue. Meantime, I will share the codes. It's the same data set that I have been using, but for the final phase of the work, I'll be using a data set of called EOF. Just please keep that downloaded as well with you. So it's 7:30 p.m. now. We'll start around 7:40, 10 minutes. Okay. Oh, sorry. It's pretty much a Sri Lankan time now. Yeah, it's 3 p.m. So we'll start around 3:10. Uh, Chamot, someone asks about the attendance link. Do you have it? So sorry, I don't have the attendance link. Let me check. Oh, sorry. Yeah, okay. I'll give you 15 minutes break now. Okay. Meantime, if you have a question, you can directly message me. No problem. I'm online, so you can text me if you have a something to be clarified. Because don't keep any doubts just because I'm asking whether it's clear or you're saying yes for the sake of it. Just don't be like that because you all have paid for this and we need to make sure that you are getting the maximum out of it. Just use the chat if you have anything to be clarified. Okay, someone asking whenever they are applying for PhD opportunities, Python is a requirement, or else machine learning, I would say data science in many of these projects. How can he or she learn this without any real projects? Yes, learning theory, I would say first thing come to your mind is doing an online course, which is absolutely useless. So if you do a course by Andrew Ng, I'm not saying they are not great. They are the best. I mean, they are considered as the machine learning giants or else as experts. But we need to understand which background are we from. We are from civil engineering background. So many of those concepts, the maths behind those, they have learned it for 4 years, but we have not. So if you want to use some model or need to optimize some model, so it's not going to be that easy as they say. So obviously that path is closed. So then it comes to the second option. What I would suggest is go for a online data repository. Okay. Data repository like Kaggle or Mendeley. Find those, especially Kaggle. If you go to Kaggle, you would see house price data set and many data sets like that. So you can try what I have been teaching you so far. So use these skills. How to open a data set, how to append a data set, how to combine few data files, how to draw them, how to find the patterns, so how to cluster them, how to fit a regression model. Learn those skills because doesn't matter what we teach, we only have a limited knowledge other than our main stream, which is civil engineering. Okay, so that's the best way to learn. If you want to swim, jump into the water. If you want to learn coding, coding. That's it. No point looking at online courses and spending your money. You will listen to those, but unless you do it for yourself using an actual data set, you will not actually learn it. Because when you are doing it, you will come across, okay, this data has outliers. How can I even open this file? And this is the exact reason this course was suggested, developed in a way that we do the coding for you and show them how it's done. But remember last week I mentioned it's only better for you if you are trying these by yourself. So that's the second path, which is the best path. And since you are asking Python as a requirement, nowadays Python is not a skill. Python is not a skill at all. Because AI tools have taken over it. Whenever you ask a code, ChatGPT or Gemini or Claude can give you the code. But if you need the codes, don't use ChatGPT or Gemini. Use Claude. Claude is the best for coding because it has been developed for coding purposes. Claude is the best if you want to develop some codes for your requirement. For that, if you are, let's say, if you are developing a model. Now, if you asked Claude to develop a decision tree, so that will give you many hyperparameters and training, testing, whatever the split that it um, it suggests. Unless you know what these parameters are. That's why the knowledge we offered you are important. Now you know what should be done to the data, how you should open data, how you should clean these. So whenever Claude give you something, if there's a step missing, you can ask, okay, this should be there. these data outliers should be cleared out. So then it will say, yes, it's a good suggestion. Then it will give you the directions. Likewise, uh, this is the best way you can learn or expert these coding requirement. Go to Kaggle, get a data set, and please repeat these coding what I have been doing so far as much as you can. And that will be enough for your PhD opportunities just for the entrance. But if your PhDs can be related to maybe image data or any other technique, you have to learn it in the same way. Did I answer your question? I did the same way. I did the same way because my Python knowledge was very poor. So there's something called and more to a PA1 or project. So those things, I think I got 10 out, 1 out of 10 or something like that. Very weak. I was very weak in Python, which is why even though I could have CS, I did not want to go to CS because I knew my coding was relatively lower or else poor. So by the time I did civil engineering, so when Professor Dias introduced this data science module within the MSc, so I realized there's a scope like this which we can use data science in civil engineering. So what I then did was, uh, with the instruction of ML students, you need to have such students like OS, at least friends from your computer science background. Otherwise, you don't know what you're doing is correct or wrong. And try to develop these codes and what you have been doing so far. So that will help you to get an initial understanding how this model predictions and everything. Once you understand that, then go and read a bit more about the mathematics in each um, specific model. Okay, so for example, if it's a decision tree, go and learn or go and watch a YouTube video how this tree works. Okay, does these parameters influence? How does this affect the model? So by doing that, you can understand how which parameters I really need to control, and likewise. So with time, so this is not 1 month or 2 month process. This will take at least few years. So that's the best way if you want to expert as a skill, especially the data science from a background of civil engineering. So for your reference, I hope you can see the uh, Kaggle page. So this is compressive strength data set which we used and we have been using so far. So if you want to download that data set, you can press this one and you just need to log into Kaggle and download it. And if you need to see some codes people have developed, you can see this, sorry, not data card option, code. So there are 38, notebooks are there. So there can be many different, some of them are informative. You can see, even you can find the codes if you need to learn. But once you get these kind of code, you are in a bit of trouble because you don't know what these lines are mean. For that, you can use something like Claude and give each cell to Claude and ask it to explain what does these lines mean if you don't really understand those, and explain to you one by one. So that will do, and you will have an idea, okay, what this code does. So this is also the same compressive strength data set, and I think they have modeled something. So long code. Yeah, then they are checking whatever the Pearson correlation and everything. Don't know whether the R squared values are there. Let me check. Yeah, not a bad model. They have 10 good predictions. Yeah, if you want, you can download these ones as well. Let me know if you all are there, then we can start again. Give me 5 minutes, then we'll start, okay? Shall we start? Are you guys there? Hello. Can you hear me? Yeah.
Yes, sir, we can hear you.
Yeah, okay. So just an additional note. So you can always go to Kaggle and there are house price predictions. So this is the most simplest data set that you can use for machine learning, house price prediction. There are only few variables. And whenever you see these codes, now you know at least what these are. Okay, if you see these things, you know, okay, these are the libraries that we need to import. And something like this, if you see, okay, so this should be the data set. And then this, there are alternative ways that you can do these things. I think they have already defined training and testing CSV. That's why they are calling like this. But anyway, now you know most of these codes and what they really means if you need to drop any column and their shapes and everything, plots. They must have done many additional analysis as well, correlation. This is what, yeah. See some of the models they have. Is that model? A model, I think. So anyway, you can use those. Just an additional note for you. And we'll go to the notebook again. Can you see my notebook?
Yes.
Yeah. So now we'll go to the ANN model. Last time I told you, especially kernel-based models like ANNs, KNN, and SVM, we need to normalize the data. We'll scale the data. So here I'm using standard scaler. So let's just run it. So now I'm developing a function for, I have developed a function for the function for plotting actual versus predicted. This is that function definition. That's it. So now I'm developing or trying to develop a neural network. So what these models or what these lines mean actually. Now, unlike a previous model, so these are the essential libraries that we need. Okay. So we need TensorFlow and Keras. So this is not the scikit-learn neural network, which we call MLP, multi-layer positron. So we are developing it from the scratch. In the scalar, I mean the neural network available in a scalar, there are few hyperparameters. You can't modify it too much. That's the reason. So if you need to customize your neural network, you need to use these libraries and build it from the scratch. So in this case, I'm developing a model from Keras sequential neural network model. So I have commented here. So this is the input layer. I'm taking X trained scale. Shape means the array shape. So for example, how many input nodes it has. So in my case, I think it's 9. It was 9, wasn't it? Is there 9 inputs that we used? Can anyone reply to that? 8. Okay, sorry. 8 inputs. Someone says, okay, 8 inputs. Then I have defined a hidden layer. Okay. So now you know what is this activation means. That's a nonlinear activation. So in this case, I have used ReLU. I think ReLU does not allow slight negative values, but if you use leaky ReLU, it does allow slight negative values as well. So we can't exactly say what is the correct activation function for just for the time being. It's first case or maybe initial trial. So we are using ReLU, and now number 16. Can someone can ask, okay, how did you come up with number 16? That's a good question, but let's first go with this hidden layer. Okay, so it only has single hidden layer and one output, which is the compressive strength. Okay, so when you model, you need to compile the model using an optimizer. I'm using Adam, and loss function as mean squared error. Okay, so I'm asking now to fit the model using X train scale and Y train using a validation split of zero point 0.2. So whatever the data amount comes to training, let's say it's 70%. Out of that, 0.2%, I mean 0.8% of that one is going to actual training, and then 0.2 is gone for the validation split. So this epoch is the uh, number of iterations that we get the error and then feed it back, optimize the network weights. So batch size means how many chunks of data are taken at uh, each training. Okay, and then I'm plotting the loss function. So usually when you have a neural network, unlike in previous models, first what you should do is plot the loss function. That's the best option you can do. Okay, and then you obtain the predictions similar to what you did in previous model, but it's a bit different because of the scaling. Some other parameters have been involved as well, and similar to earlier, you can get the performance indices uh, using the data. Now let's look at the loss function. We did not still talk about why we selected 16 neurons. Let's come back to that later. So now this is the loss function. So it's mainly the error between actual and predictor. So you can see at the first iteration, the model is not good at all. The prediction between actual and error in the training or maybe the validation set. So it's very large. So with iteration, it will converge, but it will converge to uh, 200. So it's not a very good number. You can see it from the R squared value. It's not overfitted, but it's not a very good model at all, which has a poor performance. And this shallow network, so it's only one hidden layer of 10 R squared of 471. Okay, the same model. Now I will be using 3 hidden layers. Okay, so there goes the same libraries. So there's the same coding for the model. So input layer is there. So the hidden layer is there. Something called dropout comes here now. What does dropout mean? So this is something you can use for overfitting control. Dropout means you randomly drops a fraction of the data while training. So if this dropout set has the overfitted, model might not learn based on those variations, which is why we can use this to improve the regularization. Okay, so if this is 0.2, that means 20% neurons drop 20% of the neurons during training. So if it is 0.1, that means 10% of the neurons dropped during training. Okay, so the connections are there. It's just that we drop that loops. The part of the neurons. Now we are adding another layer, hidden layer 2, with a dropout rate of 1. And we are adding another layer. And for fun, let's just delete one layer and see what will happen. So it will have 32 neurons in each and 2 layers. Just remember this number, something around 86. Let's see what will happen with 2 layers. So you can see it takes time. So this is the exact reason. So it's just only, I didn't even optimize it. This is model training, right? So it's 0.6 something and 0.6 something, which is very, comparatively good compared to the single layer model. Okay. So if I go for 3 layers, yeah, the loss converged something around 34, which is okay. The mean absolute error is like 5 megapascal. Reasonably good model, I would say. zero point 0.8 is there test for testing. Yeah, not overfitted. Now, so you will see when you increase number of layers, accuracy will improve, but the problem is you don't know how many layers. There can be a 2-layer network better than this with slightly different neuron arrangement. Maybe in a single layer 10 and the other layer 14. You don't know this one. This is the scary part with working with neural network. Let's say how many parameters we need to optimize. If we need to optimize, we can optimize number of layers. So it's just one parameter then. Okay. We can even change the number of neurons inside each hidden layer. Okay. Say, for example, in the first hidden layer, we can have 10 different neuron arrangements. In the second hidden layer, we can have 10 different neuron arrangements, and in the third. So this will give you 1,000 combinations. So that 1,000 will be multiplied by number of layers that you can change, if I'm correct. Because you can have even 1-layer network. You can have 2-layer networks and change neurons in each 2 layers. And then you can have 3 layers and change many combinations within that 3 layers. So approximately I would say more than 1,000. Okay, obviously more than 1,000. So now if you want to check learning rate as well, there's no influence, there's nothing that you can explain such as influencing parameters in an ANN. They will completely vary based on your data and their distribution. Okay, so no one can tell you what is the best, not even God can tell you what is the best configuration of ANN for this dataset. There can be 2 completely different ANN configuration which will give you same accuracy for this one. So now 3,000 models, and then if you want to change learning rate 5 times, it's becoming 15,000. And if you want to change number of batch size, chunks that you are using in training, again 50,000 multiplied by another number. And there can be various parameters. If you need to change the activation function, maybe 2, then it becomes more than that. This can easily become 1 lakh. So you can see this how large grid can be made if you want to optimize a neural network. This is just uh, totally different from the tree-based models, because in tree-based models, I could tell you, okay, tree depth and estimators in ensemble models mainly governs the performance. So now you know, okay, if I control these two, I can mostly get it done within a short period. And training of the tree-based model, you saw just when I click it, I get almost the prediction. But in this case, when the neural network becomes larger, it takes more time. Even based on your data set, it can take maybe 1 or 10 or 20 minutes to train. So imagine if you want to optimize a network which takes 20 minutes to train, and if you need to operate or else evaluate more than 1 lakh models. So it's 1 lakh models into 20 minutes, let's say half an hour. So it becomes 50,000 hours using the available computational resources. So this is why working with neural network is not exactly easy as it looks. Many people turn to tree-based models in structural engineering because of this, because tree-based could give you good predictions, I mean comparatively good predictions in a very short period. But it doesn't mean that ANNs are far more behind or lagging, because once, or if an ANN model is properly optimized, it could be maybe fairly better than tree-based, or else comparable to the tree-based. So it's up to you to decide which models do you like. Now we'll go back to how you selected this number. There's no specific guideline to develop the number of neurons. First, thumb rule based on my experience I could tell you is start from single layer. Start from a single layer. List the numbers that you have to optimize. It's easier for you. Start with a single layer and change the number of neurons. So now how I can decide the number of neurons, because it could be anything. Uh, for this, there are few thumb rules. Some of the people say like get 2/3 of the data size of the data. Or else I myself have been using the multipliers of square root of inputs. Say, for example, if I have 8 inputs, the square root is something around 2 point, what is the square root of 8? Like something closer to 3, right? 2.8, maybe 2.7. So I would say 3. Okay. So then I will use multipliers of 3. First, I will go with 3, 6, and 9, or else maybe 30, 15. Likewise, I will see and try to increase the number as well. See if it can give us a good prediction. At some point, if you figure out that it is not sufficient, then go for a 2 layers. Okay, that's the main path that you should take if you want to really develop develop an AN. Still, you should not be increasing too many layers. The reason is, here you will see a code line. I have given you a model summary. So now 32 and dense layer, 3 layers are there. So in each model, there are this much of parameters, okay, creating. So the total number of trainable parameters is 2000, right? So it's a fairly large number compared to your training data set. Some people suggest that this number should be less than uh, the number of training data points, but it is not strict. I mean, it is not strictly considered, or it does not hold strictly, because modern neural networks have regularization parameters, so that even if it's beyond that, you can get a good performance. So it's only a thumb rule. Okay, but you should not be increasing this too much. Say for example, now you have 700 data points and trainable parameters is like 1 million. So what will happen is you will get a good accuracy training. What actually network does is, rather than learning, it will memorize the data, because it has 1 million parameters, 1 million neurons, or maybe, sorry, 1 million parameters, or many neurons. So it doesn't need to learn. It can memorize these data and give you the exact prediction. So it pretends like it has learned everything, but it's not. Once you give the test set, you will see the model will be overfitted. This is something you need to worry about ANNs. You should not be increasing the number of neurons or number of layers too much. You should work with as much as possible lower number of layers, and see you can figure out. And one important thing is, here it's 32. If I increase it to 33, it can be a totally different, totally random performance. Can be even reduce the performance. So it does not add up, or like in trees, you saw that when you increase the depth, you could see some impact on the performance or else converging behavior. But for the ANNs, it's completely different. If you use this to a different number, you will get something completely different, because now the model is different, connections are different, gradients and all these chain rules. So the mathematics happening inside the network become completely different and will end up in a completely different performance. It's just not like the how trees work. So if you increase the depth, you know that the same tree, so we add another layer and we divide whatever the existing amount of groups. But in neural networks, it's different. So I told you how to decide this number. That's a thumb rule. I usually use the square root, multipliers of square root of the inputs. Okay. So, and epochs as well, you can go up to 200 to 500. It's a safe iteration number. Unless until you see those two are converging. Let's say your training curve is like this, testing validation is way converging around 600, so that will give you, definitely it's an overfitted. Sometimes you will see training curve, loss curve is very smooth, but the validation is not. It has certain abrupt fluctuations. That means your network is not the best. You need to optimize it. So training a neural network, always a challenging task. For the optional, if you use this same data set in MATLAB and ask it to fit a neural network, you will see almost 99% training and validation accuracy. Why is the reason? In MATLAB, already there are many functions performing. For example, it normalize, it transform the variables sometimes. The one I told you, like log transformation or something like that. So it optimizes the network within itself using many mathematical operation, which is why you get a very good prediction, because you don't know what even that layers arrangement or is what's happening inside that network within the MATLAB. But if you want to develop it from the scratch, it's a challenge. So there are two options. If you really need, if you don't care about the architecture or whatever, if you only care about the prediction, you can easily use MATLAB. It will give you good predictions. But if you need to develop your own ANN model, you need to develop it from the scratch. but you can get help from maybe Claude. Okay. So is that clear to you, or any questions now you have? Any questions you have? Because I think we have, how long do we have? Is that 2 hours or 3 hours? Someone? Hello? Any question you have? Or is that clear to you? At least certain extent? Okay, in that case, we'll go to model explanations. So we did these examples, how to optimize XGBoost using grid search and everything. And now we have these, what do we call inputs, and I just develop a random XGBoost model and then use this one, maybe second model. So it's not fairly overfitted model. It's like 87 and 92. It's fairly okay. But this one is looks clearly overfitted. So once you uh, run this 100 line 120, it uh, replaces this XGBoost model as the latest one. So this one, okay. So it XGBoost regression is not no does not mean that the depth with 5 unless if you run this code. Okay, so whenever I call XGBoost regression model, it means the number of estimators 10, depth is 5, and gamma equals this amount. So now I obtained this training and testing scores. Okay, fairly okay, R squared values. Now, if I try to convince this to a structural engineer, what are the problems that you will encounter? So now you all are better structural engineers than I am. Now you can answer that question. If I'm showing this to you people, what are the questions that you can ask from me? I'm saying, okay, this model can predict compressive strength data. So are you going to believe me, or what are the questions that you will have? Anyone? I know many design engineers are here, so they can always engage in the conversation. Please do so. So even with this accuracy, let's say it has a good accuracy. So what's the problem with now? No problem? Anyone? So if I say you this model, you can use it for design or to calculate compressive strength, you are just going to use it as it is. Is that what your decision is? Anyone thinking of a question with this model? Okay, someone asked safe. Okay, that's another problem. Another important problem. Now, okay, let me give you two examples. Okay, you know how to come up with a certain compressive strength using a mixed design, how to develop a mixed design. Okay, you have that calculation. Okay, that's the first method. The second method, I'll give you all the inputs like this and show you this is the model which you can't see at all and arrive with the prediction, target strength. So, comparing these two models, what's the issue? Let's say I ended up with the same, let's say I ended up with the same exact strength or maybe similar, similar mixed design parameters. So then what's the issue? Can I convince a structural engineer that we can use it? Yes, safety is there, but it's one concern. Other concerns? Standards and compliance. Standard and compliance is something that you can regulate within the model. Let's say you tell the model, okay, these are the compliances that you need to satisfy. Okay. That can be done maybe in a later stage very easily using the model. But there's one bigger problem still. Anyone? So there are two aspects. One was the accuracy. The second one was explainability or is the interpretability. Explainability and interpretability does not mean the same thing. Interpretability means how interpretable is the model itself, and explainability means how we can explain the model predictions. So for now, we'll check about this one. Say for example, let's share. So the second aspect is explainability of this machine learning techniques. How if you show this to a structural engineer, first question you get is, are these physically reliable? Can we explain these predictions? How can we know what's happening inside this model? This could be giving a prediction with something completely different relationship. So we need to explain the model for that. For example, now imagine this one. Now you have a black box model, what we call a typical machine learning model. So now you give an image of a butterfly. Okay, model predicts it as an insect. Okay, that's what you are getting. But why the model predict it as an insect is not known, which is you need as a structural engineer. Otherwise, accuracy could be, I mean, accuracy could be anything, right? It can be conceiving, it pretends to have a good accuracy, but interpretability or explainability will show you how good a model or how physically consistent model it is. In this case, if we use explainability component outside the model once it's trained, so something like this could be obtained. For example, because it has six legs, I predicted it as an insect. So now you know this model predicts insects based on number of legs, right? If it has six legs, okay, it's an insect. Same concept can be applied to concrete as well. So for that one, remember I called you interpretability. So simple models like linear regression and shallow decision trees are interpretable. In last week, you noticed that linear regression has its own coefficients. You can see it's fully interpretable. And decision tree has shallow depth. You can see how the decisions are made. So it's interpretable. But when the depth increases, it's no longer interpretable. You need explainability techniques to explain the model predictions. Sometimes we call them post hoc explanations. So once the model is trained, we apply a separate agent to explain. One such agent, one popular agent is Shapley additive explanations. There are other popular ones called Lime as well. But now we'll go to the notebook again. Can you see the notebook? Quickly, someone.
Yes.
Okay. So I'm using SHAP, which is I'm importing the library. So explainer, in SHAP, there are few explainers. For decision trees or any model, you can use this tree explainer. But for neural networks, I'm not sure this tree explainer will work. For this, you need to use kernel explainer. Not even deep explainer. Kernel explainer will work for, I think, most of the models, but tree explainer is something very fast and can be used for many models like decision trees, random forest, and XGBoost. So I'm explaining the training data set. Okay, so explaining that predictions, let's see. Okay, now don't worry about the colors first. Let me uh, go through each and everything. So now in the left hand side, you can see the parameters or else the inputs we used in their specific order. So the ones on the top are the most influencing parameters, and ones on the bottom are the uh, least least influencing parameters. In this case, you can see age is the dominant factor, even though we can't change it, right? We know age is something we can't control, but all other things we can control it. Okay, bear with me now. Age, you can see something called Shapley values. Okay, this is a unified index. It doesn't have any units. It's giving you certain magnitude of impact. If you want, you can normalize it and make it a percentage. That's up to you. And for each age, you can see these dots are blue and these are slightly purplish and this is red. So this red means high and low. I will tell you what is high and low. Now, in age, did we describe the age? df describe. Okay. Now you can see in the age, the minimum is 1 day. right? Maximum is 365. Okay. So now the values closer to 1 are called as low. Values closer to 365 days are noted as high. So whenever red color appears, so that means that feature value is closer to 365. It does not tell you exactly the number. Um, it's closer to 365. Blue means it's closer to low, right? So whenever low, you can see negative SHAP values. So what does that mean? So whenever you have H1, is that negative compressive strength? No. SHAP, what does is, it's like a game theory. Say for example, what it does is, inputs are taken as players, prediction is taken as the game. So it calculates each player's contribution to the game. So in each case, SHAP will provide specific prediction called base value. It's a constant throughout each row. So even if you have 1030 data set, base SHAP will produce same base prediction for each row. Okay. Now let's say a particular row has um, age of 1 days. So now this base value will be forced by somewhere closer to minus 20 SHAP value. Okay. Now let's say it has a cement content of higher cement content. Again, for the highest cement content, the corresponding SHAP value, let's assume it's 20. So now let's say the base value is 40. So it was reduced by 20. It is now 20. Again, it is increased force to the positive side by 20. Now it's again 40. Likewise, this will be forced based on Shapley values and arrive at a particular prediction. So in this case, this is we call global explanation. So this is the explanation for the whole data set, whole or what we use training data set over here. If we use capital X, so that will give you all data points. This will explain the dataset in overall manner. Say, for example, higher with age, I can say compressive strength is going to be high because those are positively contributing to the prediction. So whenever I increase the cement content, you can see contribution is so high means higher cement values, higher cement content, low means lower cement content. So whenever I'm increasing cement content, so model impact becomes negative to positive. So that means it's increasing the compressive strength whenever I'm trying to increase the compressive strength. So slag has the same behavior, but water, have a look at that. Water, whenever I increase water, what will happen? Compressive strength will decrease. Does that or will that hold with whatever you learn in civil engineering? Is that correct? Anyone? Anyone? What do you think when you increase the water content, compressive strength increase or decrease in general? Decrease, right? So what about the superplasticizer content? So this says if you increase the superplasticizer content, it will increase the compressive strength. So which agrees with whatever you have learned or whatever the general accepted engineering principles. So using these explanations, right, you can sort of understand the model, how the model takes the decision. So what this explanation gives you is how the model thinks, right? How the model arrives with a prediction. So the reason fly ash and coarse aggregate has relatively low contribution is not something to do with actually coarse aggregate and fly ash. That's why you need to check the distribution. See this for yourself. Now, coarse aggregates, where's that? Coarse aggregate minimum is 800 and maximum is 1100. It is the variance of that coarse aggregate is pretty much less. It's why, that is why SHAT doesn't have enough variation within the coarse aggregate to give you a good explanation. So whatever you give to the model, whatever the model has trained, whatever the data model has been trained on will be explained using SHAT. Okay, whatever, so everything comes back to data. Even if you explain, even if you put garbage data, this will be a garbage explanation. This is why you need to make sure the data you have are in good quality. Okay, this will give you some sort of understand whether it agrees with known engineering principles. One example that you can do is try um, try randomly edit compressive strength, maybe uh, like a outlier, and train the model. Even if try to make it an O of it, exact O of it, and see what will be the explanation. It will be completely different. This is why you need to make sure if you if you accidentally explain an overfitted model, Shep doesn't know the model is overfitted or not. It will explain whatever the garbage that givens to that is given to Shep. So from data onwards, you need to maintain the quality and statistics and outliers and pre-processing part, everything. So it's a connected pipeline, and you need to ensure model is not overfitted and properly trained. And then you can safely use explanations to further verify, does this adhere to known engineering principles. Say, for example, this is the global explanation. Now I will go to local explanation. So I'll take a random data point 10. So this 10 means 11th row in the data set. So if I say 0, it's the first mixed design or first row. Okay, 10th data point, which is the 11th row, I will explain. So it will give, okay, from age, it will have a contribution of this much, and water, this much of contribution. So it's not always negative. So this is a single data point. This is the overall impact, right? Overall, how the water will affect. But this could be a certain instance like over here. At that particular instance, that particular water content has contributed to increase its strength by this amount, right? So any of these mixed design, if you have 1,000, all these 1,000 can be separately explained. This is why machine learning is actually useful. Say you have a complex design that is governed by 10 or 12 or multiple parameters. You can't exactly say what's the impact of what's the actual impact of this parameter. Then you can safely use machine learning or data science techniques and then explanation techniques to figure out what parameters do I need to decide, optimize my design. Before doing that, at least if there is a known parameters, you need to verify the impact of that known parameters adhere to your knowledge or whatever knowledge that you have gathered. Otherwise, if none of the parameters are not known to you, no point of using explanations, because even you can't explain the explanations. Is that clear? Is that clear to you? Hello? Okay, one said yes. Others?
Yes, clear.
Okay. So this has become an important part in machine day-to-day applied machine learning. So whenever you optimize a model, or if it's a properly trained and validated model, you need to explain its parameters, how it impacts. Say for example, uh, if you have this model, let's say you are doing some certain design, you need to change one parameter and see its impact. So if you have those data, prior data, you can easily run a machine learning model and see the impact. If I change this one, what will happen? Rather than going through a complete new design calculation, you can easily get its impact as a pre-engineering judgment. The term pre-engineering judgment. This is not an exact answer. This will guide you towards a, an early judgment. Okay, if you do this kind of a design, it will give you the target prediction. Okay, this is why you have to use sensibly these things with whatever you know. The AI is not to replace your judgment, it's to assist or maybe help your judgment in the early designs. It's never going to replace you. Or and here I have explained all parameters. I mean, no, each variable, how sharp value means their impact. Okay, nothing more. Their impact. So this negative means it's not uh, going to minus compressive strength. So there it's an impact value. Okay, so compared to the base value, so this is going to force this base value to the negative side, so else the decreasing compressive side. Okay, so let me check. I can get the same force plot for the instances. Yeah. Something wrong with my JavaScript, but this might work for someone else. Sure. Yeah, it's omitted in mine, but keep this line with you. Sometimes it might work. It will give you something like a line, how it's pushing each uh, pushing the base value, and it will show you what is the base value as well. Let me give one last try. No, it doesn't work that way. Anyway, I'll keep these lines. So it's the same plot as this one. Okay. So it will be a single line showing that from the base value, how these values are forced. Same plot as this is. This we call, I think, waterfall or bar plot. There are various amount of plots in SHAP library. You can use those. So local means only a single data point or a row is explained. But global means set of points, maybe training set or a group of points are explained. In this case, it's a training set which I'm explaining. So if someone is uh, do you need to know what is this bulging area, or do you have any idea about this? What is this bulging area? Anyone can explain what is this bulging area? You can see this line is thin, then it becomes bulging over here. Can anyone explain what's that? No one. So I'll explain. More data in that range, yes, physically correct. This is how it happens usually. What actually you are seeing is a uh, distribution over here. Sorry if we can't see the entire screen. I don't know what's happening with this one. Whenever I'm trying to use it, it's just not comes in a single screen. So anyway, now let's say this is the line of H. So there are 130 or 900 or maybe 700. If I'm explaining on the training data set, let's say 790. So there will be 790 values of age. Okay. So for each age, there will be a SHAP value. So I'm developing value against their impact. So impact can be negative or else positive, right? So I get an age value, its impact, let's say zero point 0.9. Okay, it's over here. So again, I'm getting a 9. Okay, frequency is a bit more. Likewise, for each of these one, I can draw a frequency plot. What's their impact? So what SHAP does is looking at top of each of these frequency plot from 0, right? Now, if the age value represent, so let's just forget about the age value. Now what SHAP does is, okay, it converts to 1D line. Since the frequency of this part is high, there will be a bulging area over here as well, like this. So there are more points in this area compared to the remaining points. Did you get that? And for each dot, now you can connect with either it's blue or right. So if it is blue, that's something closer to 1 day. If it is red, it's something closer to 365 days. Is that clear to you? Sorry. Can you see this one? Now I can't see. Sorry. Doesn't work that way. Can you see my slides?
Yes.
Oh, I don't know. I can't see it. Anyway, is that clear to you? Whatever, how that bulging area, it's just for your information only. Just remember, whenever you look at shape, it's just not a random line. It's actually a frequency plot looking at the top. Okay, so it's a frequency plot drawn in a certain way that it has all these information, right? So that's a global plot, and there was a local plots. You can run this line and see. So sometimes it will give you. Let me see if I have that one. No, I had some other previous notebooks, which I think a few years ago. No, that's not even here. Okay. Anyway, you can try. I'll keep that code as it is. Sometimes that might work in yours. Let's see. If not, just let me know. Okay. And dependency plots. Now, this will explain each variable individually. So this is how cement content impacts your prediction. And this is blast furnace slag and then fly ash. And you can see the water content. There's an optimum content over here, nearly around 114. Other than that, when it's going to increase it further, the compression strength decreases. So this should be, or this should adhere with whatever the known principle, whatever the design principles that you already know. Okay. Otherwise, if you can't interpret, that means something else with the model. Okay. So if your model explanations are not physically consistent, or if those explanations do not agree with known engineering principle, you can't convince a structural engineer that model predictions are correct, because most of these civil engineering have been working with physically tangible or physically seen things. So if you give them a machine learning model, the first thing they would ask is, how can I trust this? How can I trust these predictions? So you need to get the predictions and explain them at least few, and try to interpret using your own engineering principles. Okay, this happened for this reason. This is why. And it explains, or it adheres with what we already know in theoretical knowledge. So now you can see the age, how it ages. So it's usually from this data we have, you can see here should be around 28 days, and it has increased even beyond that and then converging. So which is understandable, right? Early stage strength development is there, and then 20 and 50, after 50 it's almost uh, insignificant difference between the predictions, or else in the improvement wise. Now, another one. Even if you give this to an engineer, someone will ask, okay, what's the purpose of this one? I have to give it, I have to give all the inputs which I don't even know, right? To achieve a certain prediction. So this is why with explainability, how you can make this model to be useful for a engineer. Now we are here. Can you see my presentation?
Yes.
Yeah. Now you explain the things, you explain the model predictions, but it's not even enough. We'll come to this later. Now, this is where we use something called reverse learning, or else we simply call it reverse machine learning. So you get the inputs and train a model and come up with an output. Now what we are going to do is use the output and the same trained model and come up with set of input. Why this is important? Now let's say a certain input, totally random inputs, will achieve a certain strength. Now, from an engineering perspective, what you need is, okay, I need to know the mix designs that achieve target strength of 30 MPa. That is what actually an engineer needs. So if you give the model 30 megapascal, and if the model can come up with certain combinations that can achieve 30 megapascal, that would be a really great outcome. So how can we do this? So first, what we need to define is the target strength or the target prediction we need to achieve. Let's say 30 megapascal or grade 40 or grade 50, whatever you need, but should be within the training data set. That's a basic requirement. Now let's say if it is 30 and with a threshold, let's say, okay, within 30, the maximum threshold I can have is 1 megapascal. That means the predictions should be 29 megapascal and 31 megapascal. And now get a suitable input space. Now you know there are 8 inputs, so it's 8-dimensional input space. And there are certain values. Say, for example, you don't have every cement value from a very fine interval. Let's say cement can be varying from, if you check the code, like should be like 100 to 300. Let's say 100, 150, 200, 250. It's not like 100 and 100 and 203. I mean, in practically, you would not do this as well, right? There should be some practical number for the designs you would be using. So model doesn't know that. We can further divide that each variable into a finer space, right? If there are 10 cement values, we can make it 50 by dividing that into finer intervals. You don't need to. We can do this to say each variable. Let's say original variables only had five different values. So 5 into 8 variable means how much? We have 5 and 5 and 5, 5 to the power 8. Right? If everything changes by 5, there will be 5 to the power 8 combinations. But we don't have that much of data. That means we only have random combinations out of those. But still, we can make it a finely divide input space by dividing it at least, let's say, 1 million or 10,000. That is to get the model predictions in very fine intervals. That model knows how these impact changes. If it is a nonlinear curve, there can be an optimum point which we will miss in the original dataset. But since the model has the original relationship now learned, that can determine even for interpolated cases. Okay, don't worry if you don't understand, just get this concept. Okay, so we get all the predictions. Now let's say original inputs, original input data set, we had 700 training data sets. Now we make it 10,000 by dividing each variable into very fine intervals. Now let's say if it is 1 million or 10,000, we predict it for all the uh, rows, 10,000 or 1 million. So we'll get either 10,000 or 1 million predictions. So now we can sort it, okay, sort it based on the threshold. So all these compressive strength predicted would have a different value, but there can be compressive strength values which are very closer to 30. This is where our threshold comes into play. So we can now select the threshold and sort all the values, all the combinations, or all the mixed designs, which will give you a compressive strength from 29 to 31. And from that, let's say we get the best 10 or 5 mixed designs and their inputs as the mixed design. Is that concept understood or not clear at all? I'll go through an example, but before that, is that understood or is that clear? Anyone? I'm sorry, this is fairly advanced than what we learned in last week. And even though we did it in 2 sessions, this knowledge actually I've gathered in maybe 4 to 5 years. So it's very, extremely difficult to um, teach it within 2 days unless you keep trying these models and whatever I taught. Okay, so at least have you got the concept? What is meant by a reverse prediction? We give a target, we give the threshold, and we get the predictions, and we sort based on the threshold, and we get the inputs what we require to achieve that target. Is that clear? Or do I want to, do you want me to repeat? Can you use a chat, please? Because it's really important for me to know that whether you learned it or not. Okay. Some says fairly clear. Okay, others? Okay, we'll go to an example because the time permits as well. We'll go to the notebook. Can you see the notebook quickly?
Yes.
Yeah. So now I'm using same libraries and controllable features. From here, I'm removing age because it's something I can't control. Right? Does that make sense to you? Does that make sense to you? Why I removed age as an input and fixed it as 28? So I would be looking at target strength at 28 days using these variables. Okay. So what I do is, okay, first define the fixed age. So I would be looking at exactly the predictions obtained at 28 days. Okay. And then the controllable features would be these. These are the one I can change. So for fun, I would check their minimum and maximum values. So within what range they changes. So for example, cement changes from 102 to 540, right? And then blast furnace sag this much and fly ash this much. So what I do is I divide this entire space. This has 700 unique points to 10,000 data points. Divided means 102. If the next value is 110, I make in between values 104, 105, maybe 106, likewise. So just to increase the number, so the multiplication will give you a more increased samples. Why I do is you can fit a very finely changing nonlinear relationship. Why? The model now knows the actual variation. So it can reasonably well interpolate for in-between cases. So if I have 10,000 data points, okay, so the age is fixed for 28 days. So I have 10,000 rows or 10,000 mixed designs. I'm predicting, so these are my 10,000 rows, okay, which I have just created by dividing into finer intervals, each variable, right? So I'm gonna use my XGBoost model to predict, so the candidates in predicted strength, XGBoost predicted candidates. Okay, so these are the candidates. So I'm predicting all 10,000 mixed designs and their compressive strength, and give the target compressive strength should be 30. Threshold is 1 megapascal. This is 30 megapascal, 1 megapascal. So this would give me 10,000 predictions. That means 10,000 compressive strength values. Some of these values would be very closer to 30. And some would be 60, some would be 70, maybe some would be 10, 15. So using this threshold, I'm sorting the best, closest mixed designs which achieved predictor strength of 30 at age of 28 days. So these are the designs. The difference you can see almost zero. So this is something you can use for your own day-to-day engineering design, maybe in preliminary design calculations. Okay, what is the what are the set of input design combinations which can achieve my target strength? Doesn't need to be compressive strength, maybe something else as well. Is that understood? Is that now at least fairly clear or not? Okay. One set clear. Others, please. Others, is that clear to you? So we defined a target and a threshold. We divided the input space to a much larger space because the model knows the exact variation, and we predicted everything and sort based on the target and threshold and get the input combinations finally. So model says that if you use these mixed designs, you could achieve a strength of 30 megapascals. Anyone who's not clear? Anyone who's not clear? Do you want me to repeat? Is that okay to you? Suppose my compressor data set only has samples within age between 100 days, and someone asks model to predict string 10. You can't do. Simply you can't do. You can't extrapolate. You can't extrapolate in a model beyond the training limit. It's like this. If I show you, keep everything in the basics. Okay. So your model is a baby. If you show them cars, the baby will realize if he see a car, it's a car. Now, if you see a van, will it recognize as a van unless you have shown him a van? What's your answer? So this is not something physically reliable, especially for machine learning models, but this is possible up to certain extent using physics informed neural networks, because we are including some theoretical concept or theoretical equations within the loss function. So you will learn, I think there's a session maybe next week on physics informed in especially related to hydrology, because they have known set of equations as well. And but unless you use that, it's very unsafe or not reliable to use them beyond your training data range. Okay, especially trees, you can't use it. Did I answer your question? Okay, so we'll again go to the notebook. So the next only we have two topics to cover. The next one is something for you additional knowledge, which we have been researching now, how to develop an equation, simplify the equation. You don't need to go through each and every detail, but just to know there's this kind of method if you want to use it. Say for example, for that I have used this EOF dataset. What it has is certain lead channel, I think lead channel sections, their depth and flange dimensions, thickness, corner radius, and I don't remember the LS, maybe uh, something related to, no, I don't remember the exact names, but I'll share the publication where you can find all the details. And yield strength, so, and Fe means the actual strength obtained from finite element modeling. So when I run this one, let me check how many data we have. So we had around 288 finite element simulations. So so each row means a single simulation which can take up to hours. So if you are the engineer, if you ask to change one parameter, again you need to model it and run it, which can take um, X amount of hours or maybe more. But if those inputs are within this range, within these set of data, you can simply develop a machine learning model and predict its uh, for different parameters within these configuration, within these input data within seconds. But it's not what we are focusing here today. So I will use columns, whatever the applied, and then see what are the parameters. I didn't check even what are the statistics or anything, because I wanted to show you something else over here, a method. For this case, it's a relatively, its maximum depth is 3 I'm using, I think. What's that? Yep, I don't need this. Location should be good. Yeah, 99, it getting overfitted, I would say. Shall I only use this one? Yeah, what's that? Okay, not bad. Okay, now, so training testing scores are almost comparable. Uh, but you need to make sure it's not an overfit. But from the looks of it, it is not, because in 999 and other one is also 99, closer to 8. Should be okay even if you check the mean squared errors from my experience. So now we've fitted some model, and just like that, I did Shapley explanations and figure out, okay, even though there are how many inputs? 9 inputs. How many inputs actually contributes to the output? Can anyone answer? How many inputs actually contributes to the prediction? Anyone? Okay, someone says 4. Yeah, I agree with him. Okay, if you use top four input features, it would be enough. Okay, or maybe top 5. Someone he have a fairly doubt on that. Okay. Anyway, I'm going to explain all these variables. Now you can see their impact and how the Sharp value changes. For this one, it's actually no change at all in the prediction. So you can see Sharp value, which means the impact is almost zero. Thickness, this kind of variation, the reason is we only had 2 thicknesses. That's the reason. So it's showing as 2 dots, concentrated dots. It's actually 2 thicknesses we had, but thickness was the greatest contributor. You can see, right? So, and then R and all other variables. Now what I can do is, if I go to the same presentation, don't worry, it won't take long. Just bear with me. Can you see the presentation? Someone quickly.
Yes.
Yeah. Now over here, these were some totally different model. Okay, I just put a plot over here. So now we use SHAP and we decided these are the most important parameters. Doesn't mean that it doesn't need to be true all the time, but from our judgment, engineering is an also approximation. So we chose, okay, these 4 parameters are enough for the prediction. Okay, just like what we selected from previous explanation. Now what we do is, I mean, don't worry, it's bit of mathematics, but I will explain everything. Okay, so now prediction, I told you SHAP predicts something called base value, which is constant throughout. Say for example, in your compressive strength, if you ask SHAP, that base value may be 50 megapascal. Let's guess. Okay, we can exactly find that base value, don't worry, but let's say it is the base value, which is a constant. Now it's forced by SHAP value of each variable in that each row. Is that understood? It's very important. Is that understood to you? So this is the impact of each variable at each instance. When you add them all together in a particular row, let's say this is the first row, you'll have cement, water, whatever, blah, 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 their impact, sharp values. So when you add them everything and to the base value, okay, you will get the prediction of that mix. Okay, this will be true for all rows you have. Is that clear? Is that understood? But the problem is, even though we can figure out what is this base value, we don't know this function. Okay. But what we can do is the shape value is a function of the feature value. Feature value means the original input values. That's something we know. Okay. So we make it a function of original input values, what we know, xi we know. So combine that one to the original equation. Now if we have this function for each variable, we know the xi value, we know the base value, we can figure it out, we can get the prediction, and we can derive a simple formula. How to derive that was, this is just for your information only, don't worry too much. So this is, if you can you see the notebook?
Yes.
Yeah. So this is the feature value. So how D changes, BF values, WS, thickness, thickness, where's the thickness? Yeah, thickness, two values, one millimeter and 2 millimeter, and their impact. What we need is their relationship. So now the governing parameters are like what? P, Y, RS, and LS. We don't need to worry about other parameters, okay? P, looking at that, I can say, even though, yes, there should be at least few other points as well, but looking at that, I can see it's linear. That's the only thing I can say, right? Linear. I can fit a linear regression model. Then Y value, which is the yield strength. Yeah, again, it's linear. And LS and is that W? So LS and RS or W? Yeah, RS and LS. LS is there, again linear. RS is there, again linear. So I get their functions as a linear. If there was a slightly curved one, okay, we can try a second degree polynomial. But if this is a completely random function, then it would be hard. So this method does not work for all the data we have, but sometimes work in different cases. That's why you just need to know something like this exists. That's it. Okay. So if this shape can be mathematically interpreted using a known function, maybe logarithmics, maybe exponential, we can use that function to get this kind of an equation. Or in this case, it's a linear regression model I have used. So for all four variables, I got something like this. Okay. These are not the ones. Yeah. Something like this I got. Now, what I do is, now this is my original data set. All the inputs are here. Okay. Y actual is the actual prediction. XGBoost prediction also here. Okay. So SHAP values for T, Y, RS, and LS are here, obtained from these linear equations. Okay, I fitted the equation so that I know their relationship SHAP values to the original feature values. Why? Whenever I know RS, I can calculate the SHAP value of RS. Whenever I know Y, I can calculate its SHAP value because I know the regression model, it fits to that. Okay. Now we have those functions as well. When we add them everything, this is the summation, and we can subtract the summation from the actual value, okay, to get the base value. You remember we never found the base value, so this will give you the base value for first row. So essentially this base value, if your model is successful, if your model has captured at least good amount of variance, so this should be something like this, maybe averaging around some certain value. If there's many fluctuation, then you can't use this method. That's it. So in my case, it's varying around 3, not much of fluctuations. So I will use the base value as average of these differences. And finally, what I do is I add all those equations and to the base value and get a final equation like this from the machine learning model. So if someone asks, does machine learning model converted to, or can machine learning model converted to a simplified equation? Yes, now it is possible, but still we are still researching this method. We have published few works. It does not guarantee that it will work for each and every data set. Especially it didn't work for the compressive strength data set, tell you the truth. But in certain instances, there are. The value of this equation is, you can see r squared is not 99 or 97, but it's 96. Engineering wise, it's acceptable. No problem with that. The advantage of this one over a machine learning model is, even though the accuracy is bit less, if you want to develop these equation, or if you want to codify these equation as design guidelines, you can simply use this equation, because machine learning model is something uh, which is not tangible, or you can't physically see that. But this equation, even you can write this in on a simple A4 sheet and use it. So there are these methods which you can get an equation from the machine learning model. So if someone asks, machine learning model will not give you an equation. So now we know it's not always true. It can. It depends on how you use explainability in a sensible way. So that's something additional information I wanted to tell you. Let's get back to the. So anyway, I have given these codes in the notebook. You don't need to worry. If you want to learn, you can do a bit of search and see. So those predictions were not. I mean, I wouldn't say those are bad predictions. Those were good, but not as perfect as the original predictions we got from the XGBoost model. Okay. So original predictions were like, see, obviously we need to sacrifice the accuracy for this method, but for the simplicity, or as a simplified version, you can use that equation. So that, which brings me to our final chapter. So now we considered everything: explainability and reverse machine learning. Sorry. So we went there from explainable, why we need explainable, to show that model predictions are physically or theoretically consistent, which improves the end user's trust. That's the main important thing. Otherwise, accuracy will mean nothing to them if you can't convince the model is physically consistent. And then this was an additional part, how to derive an equation. And we obtained reverse machine learning technique as well. So we gave an output and came up with set of inputs which can calculate, the several design combinations if you are the engineer. And now, what we have learned so far, implementing these things, some of these, so if you look at institutes, iStruct, so they have divided several guidelines maybe called organizational readiness. So successful implementation. So overall, it says begins with clear governance and accountability. Okay. So everything should be responsible and regularly you should be updated with AI policies. And if you are extracting data, at least you should inform clients as well. Like we are doing these things, you can't just collect data without their consent, as far as I know. And then risk management, every prediction, every model comes with a risk. So what we learn so far is this is not to replace your judgment, rather to assist your decision. Okay, it can act as a quick decision tool, or maybe you can change the parameters and see how it varies your output and will help you to quickly grab the decision. Let's say you have a machine learning model, someone else has the finite element model. If the client asks, okay, what happens if I change this parameter to this one? If your model has been trained using those parameters, okay, it's just maybe 1 or 2 seconds for you to say, okay, this will happen. But if you only have a finite element model, you need to say, okay, give me 2 hours, I will go back and run this model and tell you. So which is not very time efficient if you are especially working in a time restricted, restricted project timeline. The reason these have, finite element or experiment methods are extensively not used in engineering design is they are limited time availability in during the project timeline. In my case, wind tunnel tests are rarely done. Rarely done unless it's an exceptional case, just because it takes time and resources. So it's only given less amount of time from the projected time, and even it's used not before the initial design, once the initial design has been sort of finalized. So there's no proper optimization, no anything carried out using the actual experiment data other than checking what your actual design does. And then the third one, data governance. So essentially, data should be high quality and unbiased data sets. That's the number one rule. So if you model trained with garbage, your prediction is garbage. So if you don't know that it's been trained with garbage, your explainability, everything would be garbage. So it's a pipeline. Each and every step is connected. Okay, just like the design. So if you do a calculation using an initial parameter which is wrong, so your all calculation steps are wrong. So does the machine learning pipeline is. Okay, and then the workforce training. So you need to train staff on new concepts, new algorithms, and new technologies. So it brings me to one question that someone asked, like whether these should be learned. Programming, I would say, not a skill now, since you have Claude and ChatGPT. It's no longer a skill. You can use them anytime to develop a code, but to develop that code, you need to know what you need actually. If you need to fit a decision tree, that will give you a tree. But if you know how decision tree works, you can explicitly say, okay, these are the number of data sets, so my depth should be lower than this amount. Okay, I know depth should be a controllable parameter. Please give me like these matrices for training and testing, If the data size is less than 200 to 100, do a k-fold cross validation. Likewise, based on your prompt, that will give you a more polished version compared to a general version if you asked without a proper knowledge. So that's the reason of these training course, to give you an a fundamental knowledge. Now you know which algorithms, how they work, what are their important parameters, and life cycle management. So it's a continuously evolving technology. It's not an experimental procedure, it's not a FEM. This will not replace any of these methods, but rather will develop as a single entity. But it will assist uh, FEM and experiments, because obviously we need their data. But it's a separate method. Now, if you think about, does this AI model, or do these AI models matters? Yes. You can see, if you use this link, they have developed a comprehensive design tool for maybe structural design or shear walls. Can you send us some studies to read or understand? Yeah, we'll send you a few of the articles, don't worry. And they have shown that to evaluate a one single design scheme within a day, to iterate and everything, then check their performance, it took engineer almost a one working day. Okay. So if you develop a machine learning model, so scheme n schemes with their performance could be evaluated under less than 10 minutes. So they have already marked, I think recently they said, they 5,000 completed shear wall designs for residential buildings have been done through AI. This model they have developed. If you go to this model, website, you can see it. And some of them have verified that AI generated designs are actually code compliant and engineeringly reliable. But in some of the studies, they haven't used explainable AI, which is also a must, I would say. And this was our recent study. Beyond simple rectangular designs, we have even used L-shape and other U-shaped buildings, and no column zones and voids as well. And we only gave this layout to the machine learning model, ask it to come up with a suitable beam arrangement, including primary and secondary, and for each each slab come up with a practical reinforcement layout. Okay, so this optimization was 30 times faster than regular optimization technique if you use, because you can't manually optimize these. Okay, and the optimized methods optimize material cost was the 10 to 45%. You can see how significant that is. 10 to 45% reduction in material cost compared to a conventional design, if it's a code-based or rule-based design. So this is the state of art of machine learning in civil engineering now. If you want to get updated, yes, you should. And finally, it's a two-way interaction between the AI system and structural engineer, right? It will produce some outputs, right? And you need to verify that that will not compromise structural safety. That is where your experience matters. If you know a design, okay, I had a design like this, okay, that means uh, the design obtained by this AI system is fairly justifiable and avoid biased decisions. Say, for example, especially the transparency. If you can't explain the predictions, why does it happen? Okay, these parameters should influence more. Then there should be something with the data. You need to interact with the model and see. Always it goes back to the same basics. Data quality and machine learning model is a baby. Every problem comes down to these two issues mostly: data quality and the model, how it learns. It learns from whatever it's been fed. And now, this is, I think, my final slide. So I want to ask you a few questions. The first question, from what you learn, should you allow to design a bridge without a human review, completely using AI model? What do you think? What do you think? As a structural engineer or as a civil engineer, maybe one of your designs, should you allow that to happen? What do you think? Anyone? Or is what happens if an AI assisted design fails? Any answer? Or will you trust an AI model with 99% of training accuracy? Or else, even if you, or else, if you would if you would trust a model with 99, let's say, training and testing, without explaining its predictions, and when does these predictions should be discarded or rejected? Anyone answer these questions? I like to actually see if you learn at least something from this one. Should you allow AI to take over the designs? That's my first question. Yes or no? No. What's the reason? Can you see my PDF? Hello? Can you see my PDF? The presentation? Okay. Okay. So what's the reason that you should not allow it to design? Yes, exactly. So it doesn't have the engineering intuition. So you are the driving force, right? It is only a tool that assists you to come up with a decision in a quick time, right? That you can't do, right? It's a mathematical model, right? You are the engineer. So you take the decision. So what happens if AI assisted design fails? Whose responsibility is that? Whose responsibility is that? Exactly, the engineer, right? Because mathematical or any of these models, um, what they call, they are not accountable, right? It's just only a guidance. And would you trust? Now, if someone say 99% training accuracy, will you trust that predict model? Yeah, it is not exactly overfitting, you can say, unless you see the testing data set, okay? But always need to make sure if it is 99 no more than 99, there's a risk, right? There's a risk that it could be overfitted. Doesn't mean that it is 100% overfitted, right? If the testing accuracy is very close to 99 point something, and by looking at other error matrices, you can decide, okay, this could be not overfitted, right? But by looking at only training accuracy, you can't just verify a model is good. You need to obviously check at the testing data set. But the reason for especially the number 99 is not because it's the highest, it could be fitting to uneven variations in the data. So without checking testing data set, you can't say it's overfit, but there's a risk that it could be overfitted. Okay. Now, would you trust a model with 99, maybe let's say overall training and testing accuracy, given that it's not overfitted, but still you can't explain how a prediction is obtained? Can you use that kind of a model? Exactly. That is where explainability matters, right? I mean, accuracy could be only a single aspect. The explainability is another important parameter. If it is not adhering to engineering principles, that means something is fishy. That you need to check the data, which comes to the last point again. Where should the AI predictions, even though the predictions are accurate, which needs to be discarded? So it's always comes down to data, because the model doesn't know the data quality. It will fit a relationship, whatever the garbage we give to that. So always come down to data quality. As I mentioned, accuracy could be high. Model even could be, not overfitted sometimes, but when you try to explain it, explanations are totally unreliable. So that could be um, maybe some errors in the data, right? So those errors could be everywhere, so that it's perfectly fit into the errors without any overfit, right? Let's say some variable is there. Someone mistakenly divide the whole column by 2. Okay, whole column by 2. Let's say the cement content 100 now becomes 50. Now the model doesn't know that model will fit, and it would not even overfit. Now when you try to explain it, you can't explain why this small amount of cement content would give you this much of result. But it will give you a prediction as well. No problem. Prediction accuracy is something that could be fitable to a machine learning model. But when you try to explain, those explanations are far from what is actually expected from the uh, engineering behavior. Okay. And finally, some of the best practices, always check the new inputs, or whatever you predicted is within the training data range. But if you need to do extrapolation, it is possible with physics informed learning. Nowadays, some of the researchers have proven that it's more than, I mean, reliable uh, out of the training set as well. And then you need to make sure the predictions make physical sense or else does it satisfy design codes and can be verified using another experimental or finite element modeling additional? Are the predictions explainable? And finally, would you trust this design? It's your call and your checklist to make sure the model is helping you and you know what's going inside the model. If you don't have the control, if you only use ChatGPT to develop a model and predict and explain without knowing any of this, you might have not known any of these, and you will be inside a pile of jargon. That's it. So always keep these best practices and responsibility of AI in new engineering design. It is to support you, not to replace you. So with that, I think my lecture series came to an end. So if you have any questions, you can ask. Otherwise, we can wrap it up. Thanks. Sorry, it's been a long day. Anyone has questions? So finally, it is not just the accuracy, explainability as well. There's another aspect called privacy, which is still in the uh, um, research domains, but especially in the computer domain. So it's actually the accuracy, explainability, and privacy, but or else some call privacy. So for engineers, for now, we only need accuracy and explainability. Does that make sense to you? Everything good with everyone? Uh, yeah, I think, yeah, there's only one question. So he was asking to explain, sorry, give us few documents, or else maybe he was asking research papers. Is that it? I don't know who asked those. I will send those whatever need, but yeah, I will send those. Yeah, sure. So if there's nothing, so I will end the session. Chamod, you will have the recording, won't you?
Yes, sir. So
Okay, okay,
I
oh good,
recorded
okay.
all.
Okay, then good night everyone. Thanks for joining. So you will be doing the next session with Dr. Samudhu tomorrow. Thank you. See ya.
Thank you, sir.